Good morning, welcome to today's webinar on the chocolate Turing machine with me, Sarah Zaman as your host, and Paul Curzon as your presenter, whom I'll shortly introduce. I'm one of the CAS community outreach managers responsible for managing the communities in the North East, Yorkshire and Cumbria, and supporting the community leaders in those areas. This webinar is part of the CAS Virtual Showcase, which is a 2-week window of webinars designed to support the CAS community. During the session, please use the question window on the right-hand side of your screen to ask questions. All questions will only go to me, not to everybody else, but if I feel that it's something to share with everybody else, then I'll make sure that I've read it out. All attendees are in listen-only mode. Top of the window has an orange rectangle which can be expanded or collapsed. If you're using social media today, and we'd love you to do that, the hashtag for the event is CAS Virtual 20, and I'll hand you over to Paul. Thank you.
Okay, thank you. So I'm Paul Curzon. I'm a professor of computer science at Queen Mary University of London. In my kind of spare time, I do a lot of stuff trying to support schools through CS Fun and Teaching London computing projects. This is something, the chocolate Turing machine, that came out of a CS Fun article I wrote years and years ago, that I've turned into a CPD talk. So what I'm going to do is give you a quick overview of the idea, and ultimately what this is about is what a Turing machine is. So this is something that it's actually on the A-level syllabus, I think, of the AQA, but it's something that I learned as a teenager, and actually it's something that actually you could teach to primary school kids as well. So what is a Turing machine? Well, it's actually a very simple model of computation. So what does that mean? Is it's just a description, or mathematical description really, that aims to try and capture the idea of what computation actually is. So what do we mean by that? Basically what computers can do. So a Turing machine can do any computation that any computer can do. And it was really invented by Alan Turing to explore what any computer might possibly do, to understand what computation was all about. So it can do anything any computer could do, just not as fast. It was actually created before any actual computer had been existed. So this was before the war, and it is part of the sort of foundation for Alan Turing's ongoing work at creating actual machines that led on to the first general programmable computers. So a Turing machine you can think of is a bit like a single gadget that does one fixed job. So it's like a gadget with an embedded program in. So for anything you want to do, you create a new Turing machine for it. Turing imagined these things as being something that that a human would actually operate, in that he imagined people moving the pieces around in the way that I'm going to do. So in a way, what I'm doing here is just what Turing originally imagined would be happening, because even though this is a mathematical model, what it actually is a very practical thing. You can actually build these things. So build them, yes. Not sure whether Turing ever thought of doing that, but you can build them out of chocolate. So that's what I'm going to do. I like chocolate in these times, especially. Chocolate is good to have lots of it about. Where is that idea coming from? Well, this is something you can build. The idea is computation is not something that happens on silicon. It's not something that is only to do with computers as we think of them now. What computation really is about manipulating symbols, and symbols can be anything. They can be pictures, but they can also be like my version, which is going to be made of chocolate, or Lego Stormtroopers, or buttons, or whatever else you want the symbols to be, as we'll see. So what is a Turing machine? What does it consist of? Well, I'll give you a very quick overview here. It's basically got 4 parts. So an infinite tape, that's its data. It has a head, which is just a read-write head that moves across the tape, allows you to look at different points on the tape. It has a section that is all about the state. So basically that's just keeping track of what state the machine is currently in. And then it has an instruction table, which is essentially what we would think of now as a program. So I'm going to look at how to make one out of chocolate. So I'm going to switch to looking physically at my desktop now. So hopefully, let me make this as large as I can so you can see what's going on here. So you're looking down at my desktop now. So what is a Turing machine? Well, the core of it is a tape, an infinite tape. So it's, in my case, is going to be made out of chocolate. In this particular one here, I've just got a drawing of it because actually getting chocolate that's big enough to work here so you could see it properly, I couldn't get it easily in the shops at the moment. But imagine this is a strip of chocolate, but it's also an infinite strip of chocolate. It goes on forever. So if we kind of just slide this whole thing, what you've got to imagine that this goes on to forever. How do you get an infinite amount of chocolate? Well, you just have to have a chocolate machine or a chocolate factory, Charlie and the Chocolate Factory style, churning out chocolate as you need it. So the point really is this tape has got to be big enough so that when you need more, you can add more on. If it's not long enough at the moment, it can always be a little bit longer. Okay, so imagine that this tape goes on forever in that direction. It could actually be infinite in the other direction as well. It could be going on forever in both directions. So you've got a tape. That's the first thing. Then on the tape you have symbols. So these symbols can be made of anything potentially. They could just be written symbols, or they can, as mine are, made of chocolate. So you put some pattern of data on the tape and it starts with some pattern of data, and that is basically what you're going to be processing, and that would go on infinitely. Now here I've got two symbols. I've got a white symbol and a brown symbol. What you have to do is designate one of these symbols as blank. So the tape as it's created, the empty strip of chocolate, has to have something on it, and that's the blank symbol. So here I'm designating brown as my blank symbol. It is just a symbol, even though we're calling it blank, it is just another symbol. What I could actually do is have an empty slot as what I mean by a blank symbol. I'm going to make it explicit that it is actually something there, just to make clear it is just a symbol like any other, even if you're calling it blank. So that's the core of the Turing machine. In one sense, it's this tape that's got symbols on it, that's got, in my case, different kinds of chocolate on it. What else do you have? Well, you have something that keeps track of the current state, so a state register, and you have different possible states it could be in. The tape is infinite. The number of states you can have has to be finite. Right? So in my case here, I've actually got 3 different possibilities, and again, because this is linked to chocolate factories and sweets, my symbols are just going to be sweets to stand for the different states. So I've got a green state, I've got an orange state, and I've got a red state. And at any one time, you're in a state. So at the moment, my machine is in a green state. So you have to designate some state as the start state. So my start state is green for go, and you have to designate a stop state. So my stop state will be red. When we end up in red, that just means that's when the machine stops. And then other states just have different things attached to them. You also have with the tape a head that has a particular position along the tape. So this could be made out of chocolate as well. I hope you can see I'm not sure whether in the heat that it's going to be practical for me to actually use the chocolate head, so I probably will switch over to the other version that looks like chocolate, but this could be made out of chocolate as well. So it's just a pointer that tells you where on the tape you are, because you can only read it and write at one place on the tape. Okay, so you've got that, you've got the state. The final thing you've got is a program, essentially, or what it actually is an instruction table. So it has a series of columns, essentially. So a current state, we're in the state green at the moment. It tells you what, or asks what symbol is on the tape. So what do we mean by that is what is the head pointing to? It's pointing to white at the moment, so this rule would apply. And the first columns here, I've added an extra column that is a comment, because all programs should have comments. That's not strictly part of it, but that helps to understand what's going on. So you have two columns that are identifying what the situation is, what state you're in, and what symbol is on the tape. And then you have a series of things to do. So you write a new symbol onto the tape, you can move left or right the head, and you change to a new state. So if we were to execute, if we were in this situation and to execute this first instruction, then we're in white, we're in green, so this state row of the table applies. This says we would write, we would write brown into that position, and we would move right, and we would change the state to the orange state. And so all the rows in the table are just instructions of that form. They're basically if then else rules. And that's basically it. That's all a Turing machine is, and that's what one looks like when you make them out of chocolate. So as Turing suggested, how do these actually operate? Well, it's a person, a human operator, a human computer. That was the original version of the word computer. It actually meant a human doing calculations. Here, the human just looks up what actually applies, which of these rows applies to the current situation, follows the rule, changes what's on the tape, changes the position of the head, changes the suite, and keeps on doing that until you end up in a stop state. So that's basically what it is. Let me switch back to slides again for a moment. So that's essentially what I'm showing you here. You've got the infinite tape, you've got the head that moves backwards and forwards, you've got some set of symbols that you've specified, the initial writable symbols, the allowed symbols on the tape. You've got one symbol that's a blank. You've got something about states, so you've got a current state, you've got the possible states that you've specified that this machine could be, in my case, green, orange, and red for the one I was just describing, and you've got to specify a start state and a stop state, and then you have an instruction table for this machine. So that is defining one particular Turing machine. So that's just what I've gone through there. What you can think this a Turing machine as, it follows the input process output kind of pattern that you can think of as what computers are about. They input something, they process it, and they produce output. So that's a very simple idea of what computers do, and that's basically what a Turing machine does. You can think of the initial tape as the input, it processes it, that's the operation of the machine following its instruction table, and then it produces an output, that's the final tape once it stops. So it fits the kind of thing that's taught in primary schools as to what a computer actually is all about. I'll make one health warning about this. So there are lots of variations. I mean, I've mentioned a couple already. The tape could be infinite in both directions or just one direction. The tape could move rather than the head moving. So I've been moving the head around, but it could just as easily be the tape is moving backwards and forwards and the head is staying the same. Things like that don't necessarily change what the Turing machine is or what it can do. It don't have any real bearing. But if you're doing this actually for an exam board, make sure you know exactly what the exam board expects and it's their specific version of a Turing machine that you're thinking about. I'm doing this more generally than just for A-level exams. So in practice, what does this mean you can do? Well, the first thing you've got to think about is how do you represent data? So this is a good way of introducing ideas of number representation. So we can actually use any number representation we like for this. For what I'm going to do, I'm going to keep things simple, just to keep the programs that we'll look at very, very simple, and use a representation of numbers called unary. That's just the simplest representation of numbers. So it's the kind of thing ancient shepherds would have done if they were counting goats. You want to count your goats, you put a mark on a stick for every goat you see, and that's giving you a representation. So if you've got 5 marks, that means you've got 5 goats. So here I'm going to represent 5 as, say, 5 white circles, 5 buttons. And so the number you're representing is just the number of symbols you've got. So we're back to symbols here. On the screen, my symbols are just red circles, or white circles with a red outline. In my chocolate machine, they're white buttons. They're just a symbol to represent a single thing, and 5 is represented by 5 of those. You could do more sophisticated things. So Turing machines aren't specified as only using particular symbols. When you specify your Turing machine, you actually say what symbols it can use. So you could use binary, you could give yourself 1s and 0s and blanks, you could use base 10, then you just need enough symbols to do that. So you need a symbol for 0, a symbol for 1, or up to 9. If you've got those, you can write Turing machines that operate on base 10 representations. You could even use Roman numerals or Egyptian numerals. You just have to define different sets of symbols that your tape is allowed to have, and these symbols are just the things that go on the tape. So I'm going to use this simple version of unary, and what we're going to do is just look at an instruction table, a Turing machine that would be able to add numbers. So give it any 2 new unary numbers on the starting tape, and it will add them up and give you a unary number that tells you the answer of adding them. So my starting tape will look something like this, where I've got some blanks. They're my brown chocolate. I've got 2 white chocolates. I've then got a blank. I've then got 3 white chocolates, and I've got blanks. So that's a number 2 represented on my tape, and then number 3 represented on my tape in unary. So how am I going to add them? Well, you don't think about programs first, you think about algorithms. If the head is pointing at the beginning at the first symbol, the first thing we could do is just blank that symbol and then move into the middle and turn the middle into the symbol that we've just replaced and fill that gap, and we will now have a new number that has 5 as the thing it's representing on the tape. Or we'll have a new tape with 5 on. We'll start with a tape with 2 and 3 on, and we'll on. So it's presented by a single blank, and the head is actually pointing to the beginning of the first number when we start. So how do we do that? Well, here's an instruction table that does it. It's actually the instruction table that I was showing you earlier. There's 3 parts to this. Essentially, we're starting in a green state, so this first row is the one that will apply, and its job is to convert the start of the first number. So what it does is take a white and turn it into a brown. There's then a state we'll move into where we're looking for the gap, and this is my orange state, is the find the gap state essentially. And what it has to do is march over the top of whites, and then we finally have a step where we've found the right place to overwrite, and then we overwrite the gap. So we've got 3 instructions for doing each of those 3 steps. So let's go back to my desktop and actually execute that on my chocolate. So what have we got? So I've got what I just described represented on my tape. I've got a unary number 2, 2 white sweets, a separator, and then 3 white sweets for the unary number 3. My head is going to point to the white at the beginning, and I'm going to start in a green state. So what's going to happen as I execute this, I find a row, any row in this column that fits the situation. So we're in a green state, so it's got to be a row that's current state is green, so it's going to be this first one that applies, but it could be anywhere in the table. And it says it will do something if there's a white symbol on the tape. If you find you haven't got a row that actually matches what you're doing, that's treated as the equivalent of being a stop state. It's the equivalent of being a row that says if you're in that situation, just move straight into the red stop state. So we'll just assume that. But here we're in a green, we're pointing to a white, and what does that say? It says overwrite that with a brown symbol. So I get rid of the white symbol, overwrite it with a brown symbol, and then I move my head to the right. And I change the state. So it's basically we're playing a game with a set of moves, and I've just made a move following the rules of the game, and now I'm in an orange state. So I now have to find a rule that fits this. Well, there are 2 rules this time, 2 rows that would fit this. One that says if you're in an orange state and you're pointing to white, what should you do? And the other that says if you're in an orange state and pointing to a brown, what you should do. So the state I'm in is this second one. I'm in the orange state and I'm pointing to white. So this is the rule that I will apply. And what does that say to do? Well, it's basically the find the gap. And if we're looking at a white, we haven't found the gap, so we will just move right. So its instructions are, don't do any writing. We can just leave that one alone, but move the head right and stay in the orange state. Change the orange state, but we're already in the orange state, so we just stay there. So at this point, oh, and I forgot to say, I was going to suggest you actually, if you did what you were told in the instructions and brought yourself some sweets and things that to follow along with me doing this, you can draw your own tape and draw symbols on it and rub them out and overwrite them, or do what I'm doing. But I'm a bit late telling you to do that, so I apologize for that if you didn't catch on and do that anyway. But we've now got to work out what to do in this new situation. We've done another round of following the rules. We're still in an orange state, so it's going to be one of these 2 rules that apply. And this time, though, we're pointing to a brown state. So if we were still pointing to a white state, if there was more than 2 there at the beginning, then what this second rule would do is go into a loop and just keep moving me, and I would stay there executing this rule until eventually the head was pointing to a brown state. So if I'd got a bigger number here, I would just carry on going over it, applying that rule until I get to this situation where I'm pointing to the brown state. At that point, I overwrite the gap. So I'm now in an orange state, I'm pointing to a brown. So what does the rule say to do? The rule says change the brown to a white. So I get rid of the brown and I put a white symbol there, and then I can move right. So you wouldn't necessarily have to have something that says to move there, but the final thing is then move into a red state. And when you're in a red state, you just stop. And so what I've just done is I've executed my chocolate, and in executing my chocolate, what I've ended up with is a new representation on the tape. The output of the tape is now something with 1, 2, 3, 4, 5 buttons in a row instead of 2 buttons and 3 buttons. What I've just done is added the 2 numbers that were there, and whatever numbers I had represented in unary, as long as they were separated by that single space, this program would be enough to do that. This Turing machine would take the initial 2 unary numbers and turn them into a unary number that adds them up. Okay, so that's basically all there is to Turing machines. The more complicated things you want to do, the more complicated the Turing machines are, and I've picked something very simple to get us started and just to give you the idea. But even when you're doing more complicated things, that is basically all there is to it. So what we just followed was that instruction table, and the PDF you were sent in advance does have this instruction table on. So in a moment I'm going to make you do something for 5 minutes, and so it might be handy to have that available when we get to the exercise part, just so you've got a version of this in front of you.
Can I just butt in there a little bit, Paul?
Yes.
Just about the PDF. Apologies for I sent you a version of the PDF this morning from the CAS site. Obviously, I can't seem to convert PDFs to URL, so apologies for that. If you look at the handouts, if you the go to webinar control panel on the right hand side, and if you look at the handouts section, I've put the PDF that Paul's talking about in there for you, so hopefully you can find it. Put in questions to me if you can't, but it's right at the bottom above chat. I think it'll be, says handout, so have a look in there. If you click on there, that's the PDF Paul's talking about. Thank you.
Okay, thanks. So let's go on. We've run it, and you've maybe followed along at home if you read the screen rather than listening to what I was saying. Something that's just an aside, I don't have time to go into this in more detail, but one way, if you've come across the idea of state machines and state transition diagrams, a Turing machine instruction table you can think of as just a state transition diagram, and you can draw them. So this is a state transition diagram of that instruction table that we were just looking at. You move from states to states. My states are the circles, the colors. There are various things you're looking for to allow you to move along one arrow to another state, and there are things that you do. That's a whole other talk, but it's just something I'll point you at. If you know about state machines, then it's a good thing to understand the link between the two. Something else I'll say is, just like any programs, there's lots of different ways you could do the same thing. So you could come up with a different algorithm for adding two numbers that are unary on a tape in exactly that way. So here's a different way of doing it. I'm not going to go through the details of how it does. I'll leave that as an exercise for you to look at the slides afterwards and work that out. But what this does is goes to the other end of the number and knocks off the button at the end of the number, and then goes back and finds the gap. So it traverses the first number, traverses the second number, converts the end of the second number, moves back to the gap, and then fills the gap. And that's a different algorithm. It's a program that's twice as long, an instruction table that's twice as long, but it does the same thing. You could also think of having a version of this where you really want to leave the head back at the start of the number, so that originally you had the head pointing to the start of one of the unary numbers. Perhaps it ought to end pointing to one of the unary numbers. So then you could use that to repeatedly run this table and repeatedly add numbers. So there's lots of variations. It's not the case that there's one Turing machine that does one thing. This really is like any other kind of program computer system. You can do things in lots of different ways. Okay, to the exercise I was just talking about. So if you've come with paper and pencil and that's all, you can draw a tape on paper and draw symbols on it, and if you've got a rubber, rub them out as you want to change them, just to play about with what's going on. Or if you brought chocolate along, you can make a chocolate version just like me. Or if you brought buttons, you can do it with buttons, or stormtroopers, do it with stormtroopers. It doesn't matter. You just need symbols on the tape, and you need a pointer, just something to point, and you need something to keep track of the colors, whether you of the states, whether you use suites or just make a note that we're in a red state at the moment and cross that out, and we're now in a green state. So there are various ways you can do this. I would like you to have a go, and I'm going to be quiet while you do it, just for 5 minutes or so. So my exercise for you to try, just to check you've got the idea, and ask me questions if you want, if you're not sure what's going on while this is happening. But my exercise for you to do is work out a Turing machine that always adds 2 to a single unary number. So on the tape you have a single unary number like the 5 that I had at the end, and what it does is it adds 2 to it, whatever number it is. So if 5 was on the tape in unary, at the end 7 would be on the tape in unary, and it should add it to the right hand end of the number. So basically the number should be left starting in the same place. If you find that easy, I've got an extension for you. Make the head return to the position at the left hand end so the head is back exactly where it started at the end of this. And if you find that's really easy in the 5 minutes I'm going to give you, then work out a Turing machine to double a binary number. And as a hint for that, I've said Turing machines can have whatever symbols you like. So to do that, you may find you want 3 symbols, a blank symbol, a 1, and a 0 symbol. So I will be quiet for a few minutes because I want this to be interactive. If you have a go at this, you'll have a much better idea of what's going on and what we're talking about. So I will be quiet. You have a go at this and ask questions if you're stuck or there's anything you desperately want to know.
Thanks, Paul. And just for everybody else, while you're doing this, if you do want to take pictures of what you've done and share it on Twitter with our lovely hashtag, hash CAS Virtual 20, or if you want to share it in our Facebook groups, we'd love to see them. So thank you. I'm going to go and do the exercise now too.
Just in case people have had trouble finding the handout, I will go back and make the slide point to the actual table that we started with. Or actually, perhaps I'll go to my desktop because then you can see the whole machine that I've got set up. And
Paul,
there's the table.
I've got a couple of questions. Somebody's asking, what is a unary number?
So a unary number is just the simplest form of number representation you can imagine. So I've got a unary number here, the unary number 5. I'm just using 5 symbols to mean a thing 5. If I took 2 of them away, I've got the unary number 3. So by unary number, I just mean the equivalent of what you do when you tally, except without the extension of drawing crossbars and turning them into gates. Every time you want to add 1, you just add an extra mark, an extra symbol. My symbols here are white chocolate buttons, so the number of white chocolate buttons tells you the number that we're talking about. So that's all unary is. It's basically how to represent a number when you've only got 1 symbol, whereas binary is how to represent a number where you've got 2 symbols, 1 and 0. Unary, you might have the symbol 1, and the number of 1s you've written down tells you what the number is. Binary, you've got 1s and 0s. In decimal, we've got 10 symbols, 0 up to 9. So it's just different ways of representing numbers.
Thank you.
Any other questions?
Yeah, you have got another question. I was going to leave it to the end, but you could do this one. What is a small program other than arithmetic that students might find interesting?
One thing on my website, so all the resources that go with this are on the Teaching London Computing website. So there's an exercise there that suggests why not make a Turing machine that controls traffic lights. So there you would need symbols for the colors of the lights, and you can imagine a sort of memory map version of the tape where a position on the tape actually corresponds to the light that's currently showing, perhaps, or and that is a simple sort of state transition, moving from one state to another. So it's sort of quite straightforward of how that's sort of working. So that's one kind of thing you could do that's very, very, very simple. My mind's gone blank now off the top of my head for other ones that aren't at all numeric, but something like a lift controller you could perhaps do as well, where you're kind of it's controlling moving from floor to floor. These are going away from the idea that I gave you at the beginning of a Turing machine being input, process, output, though they're more sort of embedded system machines that are real-time controllers.
Can I just ask Paul, while you're thinking about that, somebody's asked, can we see the second question, please? That was
go
on
back
your
to the
previous
question.
Yeah.
So got to get back to the right slide. I'll leave it like that and shrink the other screen, and then people who want
Brilliant.
the other, is that enough that you can actually see what's going on?
It was.
So the second part of the first question was get the head back to the start where it started. The second question, a completely different question, was double a binary number. So you assume you have a binary number on the tape and you want to be left with a binary number that's double that. The other thing you can do, so in any computers, everything boils down to binary in modern computers, and those binary numbers represent other things. So essentially, you're using numbers for anything to represent whatever it is, music or data or images. So you could start moving towards the idea of writing Turing machines that are doing any kind of thing that you might do with any other computer, where you've just got a representation on the tape for those things. Another thing, this is sort of numeric, but code cracking, encoding, doing Caesar ciphers or something might be something that's fairly straightforward if you use a limited sort of bit of the alphabet, so it's not too gigantic. Just as another example of something different you could do. Sorry, was there another question you were about to say?
No. Oh, hold on. Yeah, there is. Somebody's just said, and I need to enlarge this because it's a big question. Should this have error handling? So if, for example, there were two unary numbers on the tape divided by one brown, what might happen?
Yes, so that's a really good question. And yes, we should always be teaching people defensive programming, and defensive programming in part is where you look for what could go wrong and make sure you can deal with it. So essentially here, if there's no rule that matches, then it's treated as an extra rule that says in that situation, go into the stop state, whatever you've said the stop state is. A better program would not just crash like that, wouldn't just stop because it found the wrong situation. It would do something sensible. And whether that's error handling or just dealing with it. So in the situation where you found only one, you expected only one separator and there were two, well, the better answer to that is keep going until you find the second number. And that just means it needs a slightly more complicated program. It's arguably a lot better not to do what I've done here, just to keep this simple, and you perhaps should have rules for everything. One of the things about programming is you ought to have thought through everything and explicitly said what should happen in each situation. So if you take that idea, that version of defensive programming, it does mean put a rule in for every situation. So don't do what I've done here, which is just say that if there isn't a rule, that's the equivalent of a rule that moves you into the stop state. Put those states in so you explicitly say that is what I want to happen in this situation. You could do other things. You could sort of write some error message on the tape and then go back to the start in that situation. So that would be the equivalent of error handling code. Something else that's harder to deal with, which the infinite tape thing is all about, is what happens if the error you've got is the initial tape only had one number on it, so there isn't a gap, and you did what I just suggested, which is keep going until you find the second number. So then the Turing machine would go on forever, and it would need an infinite tape because it would keep going. So that's the problem. Well, that's leading to sort of issues about non-terminating programs and how you ensure they do terminate. So that would suggest not going on forever and have something that keeps track of how far you've gone and gives up after 5 steps if it doesn't find another number. Anyway, we're running short of time, so I'd better move on now. So I hope you've managed to have a go at that and got somewhere with it. I'll very quickly talk through my version. As I suggested, there are multiple ways of doing this, but I won't go through the solutions of the second and third part of that. I'll just look at the initial simple one. You can go to the website, the Teaching London Computing website for Turing Machines. Certainly in the slides there at the moment, there are answers to the other parts, and I'll if I've not put it there yet, I'll put an explicit versions of the others up on there, hopefully this afternoon. So an add to instruction table. Basically, it's pretty simple. It's more or less what we just had. You first want to move to the end of the number. So let's think about the algorithm first. You move to the end of the number. You then add 1 to it at that end position you've just got to, and then you move into a new state that adds 1 more, and then you stop. And that's all there is to it. So if you followed those instructions, then basically what do we need on the tape? If you're in a green state when you're starting, there should be a white there. Don't write anything, but keep moving because you're looking for the end, and stay in a green state. That first rule will loop until you get to the end of the white, so you've got to the end of the number. You're now in a brown state. So in that brown state, sorry, you're pointed at a brown symbol in the green state. So you want to overwrite that brown to a white. That will add 1 to your unary number and move on, and now move to the next state. And then you want to add the final one so that you've added 2. And so orange state, and you're looking at a brown, then write a white, overwrite that brown with a white. You've added another one on the end of the unary number, move right, and then change to the red state and stop. If you were going to move back to the beginning, you just need another state, basically, that at this point would send you back to the beginning, doing something equivalent, but in the other direction to the first rule. So that's basically all there is to it. So I hope you got somewhere through that. But as I say, you can find solutions to that and the other ones at teachinglondoncomputing.org/Turing Machine, which is the site that goes with this talk. So, sorry, question.
Oh, could you tell I was going to ask you a question there? Because we've only got a couple of minutes. I've just got one question. Would you bring up the idea of Turing machines being universal to students? And if so, how would you explain it? I don't know whether you can do that in 30 seconds.
Well, this is what I was about to do, is just mention this, and there's a longer version of this that this talk where I go into this in more detail, but not if I was doing this necessarily to primary school kids. If I was using secondary school kids, I definitely would, but I mean, it's something you can touch on at least. And the whole point of this for Turing was to explore the idea of a universal machine that can do anything. So he came up with this idea that Turing machines can be programmed to do anything that a computer can do. So it is basically exploring what is computation about, what it is possible for a computer to compute. And if you think about it, a Turing machine has the 3 components that you need to be able to do everything. That's sequence, selection, and repetition. You do things one after another, moving from state to state. The if rules that are the basis of this are just selection, and when you stick in one state, then you're doing repetition, or if you go through a sequence of states and get back to a state, then you're doing repetition. You can do everything with this. So that's the first really powerful point about this. The second powerful point, which is what it was really about, where Turing went with this, is you can move to the idea of putting the details of the instruction table on the tape itself. So instead of having to write and create a new machine for everything you want to do, which is the equivalent of kind of creating an embedded computer for everything you want to do, you can actually write a simulator in a Turing machine. You can write one Turing machine that simulates all other Turing machines anybody could ever come up with. And that just needs a representation of the instruction table on the tape. So some symbols that you're adding for exactly what is on the instruction table, like moving left, moving right, and so on, perhaps separators. You need some representation of the current state, and then on the rest of the tape, you've got just what you would have normally. And what this simulator does is kind of shuttle backwards and forwards between looking at what's in the instruction table and then going back and doing things on the tape. So it needs something to keep track of where the simulated head is as well. And that basically is the fundamental idea that this is all about, which is it says you can write universal, you can create universal computers. So this is the fundamental breakthrough. It's about the idea it is possible to write a general purpose computer. This seems completely obvious now, but it wasn't then necessarily. You can create one computer, one machine that can do everything. And before that point, and what the basic Turing machines are, create a new machine to do each new task. But this is saying one machine can do absolutely anything. And that's a fundamental breakthrough in computer science. And it basically boils down to the idea you can store a program on the tape and you can have a stored program computer. That's
Paul,
basically it.
Yeah, I may have to stop you then because we're going over, but you've got your summary and that's really good. Is there anything else you wanted to add before we close?
Nothing in particular. So that's basically the summary. Turing machines are models of what it's possible for computation to do, but you can build them out of chocolate or whatever other symbols, and this idea of universal Turing machines is the fundamental idea about it. So resources are there. If you want the AQA version of this, go to the Isaac computer science version of Turing machines. There's lots more resources there that do this in a more formal way. It's the only other thing to say.
That's
so thank you.
Thank you. Thanks for everybody else for joining us today, and thank you, Paul, for presenting. It was just amazing. I mean, you've blown my mind. So I'm sure we've had lots of thank yous through in the questions. Absolutely amazing. Excellent. My personal highlights, obviously, we're just having lots of chocolate to mess around with near my computer. Do share yours.
I now have to eat.
Yeah,
I now have to eat all the chocolate that I've been touching. So this is the good thing about this. No one else can eat my chocolate.
Absolutely.
You eat the machine after you've finished building it.
It's great. Everybody else, please do share what your examples, from the exercises that Paul asked you to do on social media. We'd love to see them and on the CAS website and the CAS Facebook groups. At the end of this webinar, a short survey will appear on the screen. We'd be grateful if you could take a minute to complete the survey. And in about a week's time, you'll receive an email with a CPD certificate confirming your attendance at this session. Recording of the webinar will be available on the CAS website in about a week. We do hope to see you at other sessions in the showcase, so please do continue to spread the word about the first ever CAS Virtual Showcase. Thank you for joining. Thanks, Paul. That was amazing. Hope to see everybody else next time. Thanks a lot.
Thank you.
Thanks, Paul. Bye.
Bye.